back to Dragonfly Engineering. So this week I got a general shop update, some of which is I've got Big Yellow in the background working to mold parts. These are more of the Game Tamer lids right here. These are polycarbonate. So it's pulling the part out and it's checking with the optical sensor that I added to the exit door. And if the machine has a part in its hand, which is now dropping off on the conveyor, then it will trigger the dual shot molding machine to cycle the round of molding again. I'd also like to talk about a follow-up to our train conveying system. So here you can see I've been running it for a few weeks now. So this section of the train with the orange cars hasn't been plucked by the robots, but the yellow section, as well as the gray section and the green section, are giving up their parts for the automation system in the front clean room. So that's pretty fun to watch, and it's nice to see that it's coming along. It still needs some development though, but we'll see how it goes. So let's walk around to the front of the dual shot molding machine and I'll show you what's molding in there. I got two different jobs with two different plastics going. So actually, since we're back over here by the gate door, we can take a look at the part checking. I see that red light on the side of the yellow robot. So that's the light from a Keyence detector, which is on that aluminum bar. And right now, the robot checked to see that it has a part in its hand. Then, like I mentioned, it goes over and it drops it off onto this to the conveyor belt here. My nice handprint right there. And then it goes back and gets ready to collect the next part. And it's in the pounce position there, and now it's just waiting for the molding machine to give it a signal that the mold is open and the second part has ejected. I also, like I mentioned, I've got a black part on the position 1 of the molding machine, and that doesn't need to be plucked like the polycarbonate part needs to be plugged, because it ejects pretty reliably, continually. Let me zoom in a bit. The second parts, these lids, it's an interesting thing. They've got a huge sprue on them, and that sprue retains heat. So if the robot doesn't pluck the part, in fact, let's take a look right now. So we'll see the red light on the robot is shining, and now it's shining on the part. And the Keyence detector noticed that lid is there, and it gave the all clear that that part is out of the mold. Anyway, so back to what I was saying. With these really big fat sprues, this polycarbonate remains too hot. So what was happening, if I just drop these parts into a bin under the mold, then the latent heat of this thick polycarbonate sprue would actually remelt the optical surface of this lid, and you would see these little shiny lines in the lid itself just from the excess heat from these sprues. So that's why we're actually having the robot pull these parts, is because I basically scrapped an entire run because there was all these little melted lines in the tops of the lids. And yeah, so the Keyence detectors, you can kind of see them right there at the end of them. Well, there's a wire that goes down to the controller, which is back underneath behind the KUKA robot. All right, let's see one more pluck here. There, it grabbed it and pulled it. Kind of pulls the stringer away if there is one, and then releases the molding machine to mold again. So yeah, let's go around to the front. So here's the other parts I'm molding. This is off a rather old mold. In fact, I had a whole episode on running this mold before. About 2 years ago. The mold is starting to wear out, so you can start to see some flash issues with the parts. So I will have to basically manually deburr all these parts. But this is the mold in the closed position. Let me zoom out a bit. And then you can see back there the yellow robot's waiting to pluck. So let's just watch this operation. So I have an air assist to eject the black part, which ejects off, and then there we're pulling off the polycarbonate, and then there's our optical test. And then the molding machine was happy with the signal that says the robot has a part in its hand. And I actually have it so that the sprue and the part are detected by that sensor. And then over here we can take a look at the controller. Here you can see how I'm using the input from the robot to close the clamp. If this molding Yeah, sorry, it seems like whenever I narrate, the vacuum hopper decides to reload. And there's the other one. That's polycarbonate in the far injection unit. And then up here is ABS with black coloring pellets. Anyway, like I was saying, so this input right here, the molding machine is using it. And it also sends an output, which I don't think it shows on that screen. So the molding machine just gave the output to the robot to pluck that part, which is too hot to fall. And then again, we ejected the black part with the air assist. That's what that yellow hairline is right there. And then we got the old temperature controller. I had an issue. I had a heater short out, so it blew out the solid state relay on this one. So auxiliary one is being used until I can replace that relay. And this ABS plastic is a little smelly. It's a fire retardant plastic. So when I start up, I actually have the respirator on because it's like got halogen additives to it, which don't smell very good. Yeah, and the drying system is working really well. I am drying the polycarbonate, and I actually have this dryer turned off because ABS has a much lower drying temperature. There goes the robot again. Actually, we can see from the back, see how it's behaving over there. And it drops it. Back home. Anyway, yeah, so this drying hopper is off, and I'm using the one in the front for the ABS because there's too much of a temperature differential between drying the polycarbonate and ABS. And yeah, we need to fix this problem too. I'm close to the end of the run, so I'm not overloading, mixing too much black in with this ABS. So anyway, that's where we're at regarding molding. So now I guess we can talk about the H-bridge circuit that I promised that I would talk about, and that's the circuit that's used to switch the direction on those train cars over there, which is controlled by the front red robot. But when the yellow robot is loading parts onto the train cars, it will control the trains themselves. And again, I can put a link to the other videos. If you're new to this channel and you don't know what I'm talking about, then that yellow robot's going to load parts into those train cars on the wall over there, and then drive them into the front clean room. And to do that, we need to make an H-bridge. So let's go ahead and take a look at the H-bridge now.
It's the question that brought you here.
What is the H-bridge?
So what is an H-bridge? Well, an H-bridge is an electrical circuit that's shaped like an H, and in the middle of the H is your motor or load where you want to switch polarity. And so basically it's a scheme with four switches that are on the ends of the H shape that will allow current to flow forward or backwards, even though you've got a single polarity power supply. So let's draw it out. Okay, so we got our motor here, which is going to be, in our case, the model train motor for our conveying system. And it's got a plus and a minus lead on it, so we can say plus and minus. And then we also have our 10-volt power supply, which would be this block here. 10 volts DC. Well, that's not drawn very well, but DC. And then it's got its leads coming off. One is plus and one is minus. Yeah, and as I mentioned, the H-bridge circuit looks like an H. So if we connect our lead here to an H shape, like so, and then on the ends of the H shape, where our motor is in the middle, we have some switches, 4 switches actually. So I'll draw those in real quick here. So, and then off of our switches, we've got, you know, the leads that come off. Now, if we want to run this motor forward, in the forward direction, then we want the current to flow this direction, so plus to minus. So to do that, what we'll do is connect the plus of our DC power supply over to this switch. So this switch is going to have current that flows this direction, will flow through the motor, and then down here, this lead, or this current flow will go through this switch. So we'll close that switch and close this switch, and come back to a point where we can connect the bottom of the H into a single terminal, and then bring this lead back up to the minus position of the power supply. So now with this configuration, with this switch closed, or this switch closed and this switch closed, our current will flow from the positive DC through the motor, because this switch blocks the current flow, and then through this switch down to the ground, which goes back to the minus of the DC power supply. Oh, and one thing I didn't show is that this, you know, this lead is not connected anywhere. But if we wanted to switch polarity in our motor and flow this direction, that means that we'd want this lead to be minus and this lead to be positive. So if we look at the flow, we need the current to come out of the positive terminal of the 10-volt power supply. It can't go this direction, and so what we need to do is connect this switch over here on the other side of the H bridge to this plus power supply as well. And now what we can do to run the power through the motor backwards is we need to open this switch and open this switch, and then we will close this switch and close this switch. So now we're in the reverse configuration of the H bridge, which is kind of, I guess, drawn by this dotted line here. This is the H shape. So it's a H with the load in the middle. But, so you can see now that our current flow from the plus side of the DC power supply will go through this lead, through this switch. It can't go through this switch, so it's going to go through the motor at the plus terminal that we've determined. And through the motor spins, current direction is opposite it was before. The current leaves the motor and then sees that this switch is closed, but this switch is open. So the current flows back to this common ground point of the H bridge and then back to the minus of the power supply. So to, I guess, illustrate current flow one more time, we'll go through the plus, we'll go through this closed switch, we'll go through the motor, we'll go through this closed switch, and then back to the power supply. If we wanted to switch direction again, then current's going to flow this way now. We open these two switches and close these two switches. So now the current will flow like this. So in our H bridge, these switches I'm replacing with solid state relays, DC to DC solid state relays, which basically act like an electric switch with transistors and things. And then in our architecture, then we've got a lead that will connect to this relay to act as a switch, and a lead that connects to this relay to act as a switch. And this would be the minus flow direction power lead. And then we'd have a separate lead for the positive flow direction. So we'd have another wire coming off this guy and a wire coming off of this guy. So now when I energize these opposite solid state relays, then we have a positive flow. And if I break these solid state relays and energize these solid state relays, then we have a negative flow, this direction. The thing with H bridges is you can never have both of these switches on each side of the H activated at the same time, because then you just create a dead short back to your power supply. So you either have to switch these two, and then you got to break that switch so that the whole circuit is open, and then you can close these switches to switch the polarity of your load in the middle. So that's very important. You can only have two on the opposite side active at any given time to have back and forth flow. So anyway, that's an H-bridge, and I've got one wired up here and we can demonstrate it. Okay, so here is our setup here on the bench. So this is basically the same H-bridge that I drew on the whiteboard over there. So we've got our counter switching, I got a little plastic in there, our counter switching solid state relays. And there's a little more wiring, you know, because you got to power each relay, and then you provide the signal for switching the relay on and off. But down here is basically the circuit of the H itself with the black and the red wires. So looking at our circuit in more detail, I've got the DC power supply over here with 7 volts, and we've got the plus and minus coming out. This extra banana plug right here on the plus side of the power supply will connect to either this connector or this connector, and this is what switches the polarity of the H-bridge setup. So when I put power to this plug, then 2 opposite H-bridges will, or solid state relays will close. The other 2 will remain open like we drew on the board, and then we'll get power which will drive the train one direction. Let's see which direction it is. Forward. And you may have seen that the 2 LEDs indicated that it closed the 2 branches of the H to drive the current, I guess, forward direction relative to the motor in this train. So now if I take this activation voltage for the solid state relays and I put them in the opposite orientation, or the opposite 2 switches in the H-bridge, then the train should go backwards. And it does. And you can see the 2 LEDs on the H-bridge solid state relays have connected, or have shown that they've created the negative flow through the center of the H-bridge circuit, which happens to be our train. So I'll plug this back into the opposite direction, and these 2 light up, which means the train is going forward. I'll disconnect, and then I will connect in this direction, and now these 2 light up and the train goes backwards. And as I mentioned, here I've got a break and then make switch, which is basically 2 banana plugs. With these H-bridges, you cannot apply power to both sides of the solid state relays, because that will just create a dead short on this power supply. In fact, we can demonstrate that if you want. Let me switch to constant current mode. So we'll do, just to be safe, we'll drop the current limiting aspect of this power supply to 0.5 amp. And I'm kind of curious to see what would happen actually with the train. I guess the train won't move at all if we dead short both of these solid state relays. And the current carrying capacity of these solid state relays is like 40 amps DC, so we should be okay. But I'm going to show what happens if you inadvertently power up both sides of the H-bridge at the same time. We'll probably see that this power supply will come to its current limit of 0.5 amp, which means that its voltage should drop to effectively 0. So we'll plug in the train, and then we will activate both sides of the H-bridge. So we've created a dead short across our H-bridge. You see the train stopped rolling, and right now we're at the current limit of this power supply of 0.5 amps, which results in this circuit of 2.7 volts driving. So normally if you just plug this into a non-current limiting power supply, just a basic DC like brute force power supply, then you would have burned up your power supply at this point, or fried your all of your solid state relays or switches. So when I disconnect the second half of the H-bridge, then the train will start moving again and everything's fine. And let me unplug it so that it goes the right way. So hopefully that explains H-bridges for you. And all of this kind of jumbled electronics is the same thing that I just drew on the whiteboard over there. And this is what I use for controlling the model trains to convey parts to the robot for automation purposes. Instead of me plugging in 7 volts to this port or 7 volts to this port, I actually have 2 lines going to an input-output module of the KUKA robot itself. So the KUKA robot applies a signal to this port or this port to drive the train forward or backwards. So hopefully that helped you understand how an H-bridge works. Well, as it turns out, as I was just finishing that last clip, we just finished the run on this part. So you can see there, cycle count 1040, good parts 1040, remaining parts 0. So talk about timing. As soon as I start recording, we finish up on this run. So now I'm gonna pull this black ABS part mold off the front, and I'm gonna reconfigure the game taming mold to run colored polypropylene in the other side of their mold. So this is a mold where you can select to run polycarbonate in the front or polypropylene parts on the back or the left side of the mold. So I'm going to do that next. So next up in the queue is more of these white ABS parts for a different customer. So this is the next day and we've got a new mold set up. But you guys have seen this run a few times, at least the people who are repeat viewers. But this is the of course, every time I try to narrate, the vacuum hopper goes off. Anyway, so these are the white ABS parts that I've been running a few times now, actually. It's always nice to have repeat orders. So I'd like to see that. And we're refilling the injection unit. And ejecting. Got a Park Glacier here coming out of the molding machine. Time to shut it down for the night. Yeah, it's starting to get up in there. Not good. Filling up. Now we got yet another configuration of this dual shot molding machine. Now I'm molding some gray polypropylene parts for Game Tamer, and then these white ABS parts are still going. So I was able to basically turn on the second mold. So we get twice the productivity now out of one machine. So yeah, I recommend getting a dual shot molding machine. You don't have to do 2 shots, but you can have 2 molding machines running 2 different products at the same time, which is always nice. Then at the same time, I've got Chewy up here in the front, or Chewbacca as I like to call it. The 90-ton boy molding machine, and it's making a product for a third customer. I call it Chewy because of the clamp sound that it makes, which we'll hear in a second. Right now I've got it opening really slow. But this is a black lid that I've shown in previous episodes. So here's the Chewy cry.